Welcome back, guys. We're going to continue on with our curve sketching unit today. And today we're going to be looking at concavity and points of inflection. I think I've also heard it pronounced as concavity. So concavity and points of inflection. So before we get started, I want you to take a look at the first diagram here. And I want you to ask yourself where there might be points of concavity. Where might the graph be concave down? Where might the graph be concave up? And where might there be some points of inflection? So just take a minute to look at the diagram, maybe pause your video and ask yourself, where's the graph concave down, concave up, and where would there be points of inflection? All right, so we're going to take a look at what concavity means, and then we're going to come back and take a look at this diagram. All right, so first of all, when we're looking at concavity, we're just looking at whether a graph is concave up or concave down. And so we have this first curve here, looks like a parabola, but this is just a section of a graph. And this graph is concave up. And if we look at the graph, as we were to make tangent lines on the graph, and we were to look at what was happening to those tangent lines. Right now, those tangent lines are decreasing. Eventually, they reach 0, and then the tangents are increasing. So as the tangent lines are increasing from left to right, the graph is concave up. So as the graph is increasing from left to right, the graph is concave up. We can check for concavity using the second derivative. So if something is concave up, the second derivative is positive. In other words, the second derivative is greater than 0. And so when we're looking at our slopes are going from negative. Our slopes are going from negative to positive. Essentially, they're getting bigger. All right, another way to think about this, if we're looking at just a diagram and we want to see is it concave up or concave down, we could think about it as holding water. So we can say it holds water. So if I were to actually pour some rain from the sky, this part of the graph would actually hold water. Okay. Now, if we look at the other type of graph where the graph is opening downwards, if we were to draw our tangent lines again here, as we draw our tangent lines, they go from being positive to 0, and then they're negative. So all of my tangent lines are going from positive to negative. So the slopes are moving from positive to negative. So they're going from positive to negative, meaning they're getting smaller. So that means the slopes are decreasing from left to right. So if the graphs are decreasing from left to right, then the graph is concave down. And so when we look at the second derivative, again, that's what we're going to use for concavity, the second derivative will be negative, in other words, less than 0. And so with concave up, we were saying it holds water. With concave down, it sheds water. So again, if I were to have a rainstorm, this acts almost like an umbrella. The rain's just going to pour off the sides. Okay, so this is kind of like our little umbrella, and it's shedding water, so concave downwards. All right, so those are points of those are the sections of the graph for concavity. We can also look at something called points of inflection. So when our graph changes from concave up to concave down, these would be points of inflection. And so when the graph is at that changing point, that's called our critical value. So if you remember with first derivative, we were also looking at critical values. That's when our first derivative was equal to 0. Well, we also have critical values for the second derivative, and that's when the second derivative is equal to 0 or the second derivative doesn't exist. And so something that's important to note, though, is that the reverse is not true. Changes in concavity occur at critical values, but not all critical values indicate concavity. And so one example might be when we're looking at our rational functions and we have NPVs. NPVs often indicate asymptotes, not a change in concavity. And so it's important to know that if there's a change in concavity, we have a critical value, but if we have a critical value, it doesn't always mean a change in concavity. Now, if the change in concavity occurs at a specific point, we call that point the point of inflection. So here our graph is shedding water. Okay, if I were to draw some tangent lines, here, my graph is shedding water. So it's above, and then the concavity changes, and now my tangent lines are starting to increase. And so I go from concave down to concave up, and that's happening at a point of inflection, okay, which often will denote as POI. Okay, over here we're going from concave down to concave up, and it's happening at that point of inflection, so POI. All right, so let's take a look back at that diagram we started off with in the lesson and try to identify points of concavity. So if we're thinking about shedding water, that's going to be concave down. If we're thinking about holding water, that's going to be concave up. And so I've got my water being held here, and I've got a pool of water being held here, and I've got my umbrella keeping me dry here, and I got another umbrella here, and I have a partial umbrella here. Now, again, you don't really need to draw those pictures. That's just sort of to give you a visual. But if we're identifying our points of concavity, we have a concave down here. We're concave down, concave down. We only see part of this, but at this point, we're going from increasing towards decreasing. So concave down, concave up, and we have points of inflection here, here, at D, and at E. Now we can write this using set notation as well. And so if we were to write this as set notation, our graph is concave downwards. So concave down. The graph is concave down from A to B. And C to D. And E to F. And our graph is concave up. Our graph is concave up from B to C. And D to E. And then our points of inflection happen at B, C, D, and E. All right, so that's just looking at the graph and identifying those key points. We're going to take a look at a couple examples here where we're going to figure out our points of concavity and our critical points using calculus. So first example here, it says find the points of inflection and determine the intervals of concavity for the function below. And then we're going to sketch the graph as best as we can with the information that we have. All right, so the first thing we're going to do is we are going to figure out our first and second derivatives. So first derivative is 6x squared plus 48x minus 5. Second derivative is 12x plus 48. And that can be factored, which will come in handy when we're looking for our critical points. So 12 times x plus 4. So the first thing we're going to do is we're going to look for our critical points. And so our critical numbers will happen when the second derivative is equal to 0 or the second derivative doesn't exist. So we're looking for when the second derivative equals 0. We can also look for when the second derivative does not exist, but in this case, that's not anything to worry about. And so we have 0 equals 12 times x plus 4. So we divide by 12, that gives us 0. X is going to equal -4. So we have a critical point at x equals -4. Now, the reason we have, we don't have to worry about does not exist, we have no restrictions, and there are times maybe where we go to take a second derivative and there is no second derivative to take. Like, for example, with a linear graph, even a quadratic, when we, quadratic, we should be able to go down and have a second derivative, but a linear function would not be able to reduce down to a second derivative. And so the next thing we're going to do is set up our intervals, just like we did when we were looking for our local maxes and local mins, except this time we're doing it with our second derivative. So we have our interval. We're looking at we're looking at x plus 4. And we're looking at what's happening to the second derivative at that point. So our intervals, if we set up our number line here, we have a critical point at -4. So our intervals are going from -infinity to -4 and from -4 to infinity. And so when we're doing this, we're going to always pick a test point. So our test point here, we'll use -5 and 0. Well, -5 plus 4, -5 plus 4 is a negative number. It's -1. So that means our second derivative is negative. If we plug in 0 there, 0 plus 4 is a positive 4. And so our second derivative is positive. So if our second derivative is negative, that means that section of the graph is concave down. And in the second section, our graph is concave up. And so we know that there's a change in concavity at -4. So the next thing that we're going to do is look for our point of inflection. And so we're going to look for points of inflection. And so we know that the point of inflection happens at x equals -4. We need to sub that into our equation to find out what y is. So y equals 2 times -4 cubed plus 24 times -4 squared minus 5 times -4 minus 21. And so if we sub all of that in, we're going to get -128 plus 384 plus 20 minus 21, which gives us 255. So we're going to have a point of inflection at -4 and 255. All right, so now we know points of concavity, we know our inflection point, and we can start to build this graph based on the information we have. We can find the y-intercept. So if we plug in 0 for x, we have 2 times 0 cubed plus 24 times 0 squared. Probably don't need to write this out to figure out that our y-intercept is at -21. But again, I'm just showing you the full steps here. So for our x, for our y-intercept, we're going to let x equal 0 and solve for y. So we have a y-intercept at 0, -21. And so if I were to have a graph here with a scale, I'm going up by 25s. So I have a point of inflection at -21. So that's just a little bit above the -25. So about there. Okay. We know that we have a critical value at -4. So 1, 2, 3, 4, 5, 6, 7, 8. So we have a critical point at -4. It's somewhere up in here. Okay. We don't know we do know. We know that that point of inflection is at 4, 255. So we've got 200, 225, 250. So it's going to be about here somewhere. Okay. We don't know anything else at this point. We don't know what our min or max is. We don't know what our zeros are, and I haven't calculated them here. We could certainly calculate them, and we haven't looked at points of increasing or decreasing. So based on the information we have right now, we do know our inflection point. So what we know is we know our inflection point, we know our y-intercept, and we know that there are points of concavity, but we don't know specifically where those are occurring. So we don't know at this point what our min or max is. We can identify where their local min or max is, but we don't know our specific min or max yet. We don't have our zeros calculated, and we don't know the sections where it's increasing or decreasing. And so that's part of what we're going to get into in our next lesson. Ultimately, we're heading towards being able to take one equation and draw the entire graph using the first and the second derivatives. So we do know that at some point we're going to cross the x-axis, and so where that happens is not totally clear yet, but it will happen. 1, 2, 3. Oh, I just realized I was not over enough. Okay, so ignore that point there. So it could come down. We know that it's going to come up at some point. It'll look something like that, but we honestly don't know everything yet. So we don't really know where our maxes and our mins are. That's going to be coming in the next lesson. All right, let's take a look at one more example here. So we have y equals x over x squared plus 1, and we're being asked to find the points of inflection and, again, intervals of concavity. So the first step is to figure out our first and second derivatives, and this is going to actually take the most amount of work because we're dealing with a radical function or a rational function here. So we'll start off with the first derivative. First derivative, I'm going to use the quotient rule. So x squared plus 1 times the derivative of x minus the derivative of x squared plus 1, which is 2x, times 1. So I know that we've done the quotient rule before, but I know a number of you use the product rule, and so I'm just talking you through this one in case you haven't used it in a while. So we have the derivative, or we have the denominator times the derivative of the numerator minus the numerator minus the derivative of the denominator times the numerator. All right. And oh, sorry there, I was checking my work there. That should say x, not 1. All right, and then we have x squared plus 1 squared. All right, so as we multiply this out, we're going to have x squared plus 1 minus 2x squared all over x squared plus 1 all squared. And if we simplify that down, we're going to have the first derivative is 1 minus x squared all over x squared plus 1 all squared. So that's our first derivative. Now we need to use that to go towards our second derivative. And so you can imagine that little mistake up there where I said I was thinking x and I was saying 1. That little mistake could have carried through and caused everything else to be wrong. So it's important that as you're doing these questions, check each step before you progress on to the next one. All right, so second derivative here. Again, I'm going to use the quotient rule. So we're taking the denominator times the derivative of the numerator. So the denominator is x squared plus 1 squared times the derivative of the numerator, which is negative 2x, minus the derivative of the second one here. So the 2 is going to come forward, and I'm going to have 2 times x squared plus 1. But remember, we got to consider the chain rule, so we're also going to have a 2x there. So we're going to have 2 times x squared plus 1 to the 1, which doesn't change anything. Again, chain rule, we've got the 2x, and then we still have the 1 minus x squared. Now on the bottom, it's going to be x squared plus 1 squared all squared again. So x squared plus 1 to the 4th. Okay, so we're going to multiply this all out and simplify. We have, I'm actually just going to rewrite it here. So we're going to have negative 2x times x squared plus 1 squared. And then we've got minus 4x times x squared plus 1 squared all over 1 minus x squared. Or sorry, times 1 minus x squared, and then that's all over x squared plus 1 to the 4th. Now, usually this is the point where I find people start to get confused. Where do I go with this? How do I break it down? And so I think I misread again. Just making silly mistakes today. Because I wrote the 1 there, I then read it as a 2. That's just a 1. And so what I'm going to do is I'm going to factor out my lowest amount. So my lowest term here, I have an x squared plus 1 and an x squared plus 1 squared. So that's going to give me an x squared plus 1 that I can pull out. So x squared plus 1, I can pull that out. And I can also pull out a negative 2x as well. So I'm going to have a negative 2x. I can pull out an x squared plus 1. And that's going to leave me with x squared plus 1 and positive 2x or positive 2. And I'm going to have 1 minus x squared. And underneath, I'm going to have x squared plus 1 all to the 4th. So canceling some things out, the x squared plus 1 will disappear, and this will become a 3. So now I've got negative 2x times x squared plus 1 plus 2 minus x squared. In this case, factoring out that negative 2x probably didn't make a big difference. So I'm going to continue to simplify here. So I've got negative 2x. In the brackets, I've got x squared plus 1 plus 2 minus 2x squared. And then x squared plus 1 all cubed. We'll keep simplifying. And so we can leave it like this. We can leave this way, or I can multiply it out further. So I have a negative 2x. A negative 2x times a negative x squared becomes a positive 2x cubed. And that's minus 6x. And then I've got x squared plus 1 cubed. Now, again, you could, if you wanted to, pull that x out again now that it's positive. So you could pull out a 2x and have 2x times x squared minus 3. And then on the bottom, we have x squared plus 1 all cubed. So sometimes factoring out that 2x isn't going to make a significant difference. But either way, you're still going to be able to get to the final step. So that's our second derivative that we've done. And we're going to use that to then find our critical numbers. So I'm just going to move the grid out of the way for now. And so finding our critical numbers, we're going to set our second derivative equal to 0. So we're looking for critical numbers. So we're looking for when the second derivative equals 0 or when the second derivative does not exist. And so sometimes we've written that as D and E. And so if we're looking for when it does not exist, that's when we're looking at our NPVs or our restrictions. So in this case, x squared plus 1 cubed is a possible restriction here. So x squared plus 1 cannot equal 0. So x squared cannot equal negative 1. And if we square root that, we can't square root a negative. So this ends up being not applicable. So there are no restrictions. And so the next part we have here, we're looking for when this is equal to 0. So we're going to look at our numerator. When 2x equals 0, and when x squared minus 3 equals 0. So either x equals 0 or x squared equals 3, meaning x equals plus or minus root 3. All right, so we're going to plug in those critical values and find out where our intervals are happening. So when we have f of negative 3, negative root 3, that's going to happen at, if we plug all of that in, just to save some work here, we're going to end up with negative root 3 over 4, which is approximately negative 0.4. So I'm doing points of inflection here, invariant points. F of 0 will give me 0, and f of root 3 will give me root 3 over 4. So we're actually looking for those invariant points right now. Now, and that we didn't do that in the last example. Now, if we write out our number line here for our critical values, I'm just going to draw a line. So if we draw out our critical values, we had those 3 points. We had a point at negative root 3. We had a point at 0. And we had a point at root 3. And so we know when we sub in our points that we're going to have points of concave up and concave down. And so in order to figure that out, we're going to have to use our interval chart again. So we're going to set up the interval chart, and we've got 4 intervals happening. So we're going from negative infinity to negative root 3. We're going from negative root 3 to 0, and then 0 to root 3, and root 3 to infinity. Now, for here we have 2x. These are our critical points that we were using. So we had 2x, we had x squared minus 3, and we had x squared plus 1. So again, we'll pick test points, and then from there determine whether a derivative is positive or negative. So the test points that I chose here, I chose to use negative 2. I chose negative 1, 1, and 2. Now, to save some time here, I've already done the calculations, but as we plug these values in, negative 2 times 2 is going to be a negative value here. So we're going to have a negative value here, a positive value here, a positive value here. That's going to make that negative. So when you're doing this yourself, you're going to have to actually go through and do all of those calculations. Now, when we plug in here, we would have a negative value, and a positive value. Well, 2 negatives times a positive is still 2 negatives times a negative times a negative is positive, times a positive is positive. And then we have a positive, a negative, and a positive. So we have an odd number of negatives, so that's negative. And then the last one is positive, 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 and positive. So if we look at our intervals here, we know that from negative infinity to negative root 3, our graph is concave down. So it's going to be looking something like that. From negative 3 to 0, or negative root 3 to 0, it's concave up, and then it's concave down, and then it's concave up. And so our concave down, if we were to write this in set notation, we could say that it's concave down from negative infinity to negative root 3, union 0 root 3, and so on. I won't bother writing that down right now. Now our invariant points, our points of inflection here, we have already calculated out. So from there, we can start to sketch a graph and get a visual of what this looks like. And so I've got the points plotted here. We're going from negative 4 to 4. We're going from negative 1 to 1. So we're going up by 0.1s on the y's and up by 0.5s on the 4s. So we can plot the following. So we can accurately plot accurately plot our origin. We know the x-intercept for the origin. We know the x-intercept and the y-intercept. And we can do that by finding finding our y-intercept. So if we were to plug that in, finding our y-intercept, we have 0 over 0 squared plus 1. Well, that gives us 0. So we know that the y-intercept is happening at 0 and 0, 0. So we can plot our origin. We can also plot our points of inflection. So we know that there's a point of inflection at negative root 3 and negative 0.4. So that's happening negative root 3. If we were to calculate that out, would be negative 1.7. So just a little bit under negative 2. So we've got half, 1, 1.5, 2. So kind of right between there. And it's happening at negative 0.4. So negative 0.1, 2, 3, 4. So there's a point of inflection happening about here. And we have a point of inflection happening at 0, 0. And we also have a point of inflection happening at root 3 and root 3 over 4. And that's happening at about 0.4. So root 3, again, just a little under 2. And 0.4, 1, 2, 3, 4 is happening somewhere up there. Now, we do know that we're changing in concavity, but we don't know exactly where that's happening yet. So we do know that the graph comes up and it's coming down, and at some point it changes and starts to go this way. And this is coming down. Sorry, it's a little tough to draw out the screen here. It's drawing down and then it changes and starts to go up. But again, we don't know the specific key points yet, and that's what we're going to be figuring out in the next lesson. So hopefully that gives you at least a couple examples. I'm thinking the most challenging piece when you're working through concavity is going to be when we get into the rational functions and just doing that whole second derivative piece. Once you have that, you're still doing the same thing as we were doing with the first derivative. Once you have your second derivative, you're going to look for your critical numbers. You're going to set up your interval chart. Once you have your interval chart, you can label things on your timeline or your number line. We can find our points of inflection, and we can do that both before or after we did concavity. And then we can do a quick sketch. So I think I kind of was messing up my words a little bit here when I was doing the second one. I was calling them invariant points. We were talking about these are points of inflection, and so I didn't clearly label that in there, so I'll do that right now. Okay, so those are our points of inflection. All right, guys, so hopefully that gives you a couple examples, and we'll see you soon.